Okay, this is going to be a really quick presentation about lenses and the lens-mirror equation, especially since you've already had some experience with the lens-mirror equation. It should go pretty fast. Okay, so the deal with lenses, they're kind of cool. You can actually think of them as two prisms stacked on top of each other like that. This is a converging lens, and they can be stacked this way, and this is a diverging lens. Some people will call this convex lens and concave lens. I try not to because I think it's confusing with mirrors. So again, we're going to talk about converging lenses and diverging lenses. When you do a ray diagram, sorry, this little F floated, I guess. If, for example, if you're talking about doing a ray diagram, which you guys have already checked out, this is the central axis right here going through the lens. This is what's called the principal axis. And then there are focal points on either side. There's no such thing as C because we're not talking about a sphere, we're just talking about focal points. And then this thing right where the central axis and the principal axis meet, this is the very center of the lens. So again, note that there's an F on each side, there is no C. And the way that lenses work is that it's really Snell's law again. Light is going air to glass to air. And so it's going through and it's bending. And I know you've had some experience with this with ray diagrams. And the equations, these are just what you've seen before because we used them for mirrors. We're using for lenses now because it's the lens-mirror equation. So 1 over F equals 1 over DO plus 1 over DI. Magnification, exact same equation, negative DI over DO, and that's also equal to HI over HO. Remember that the units for F, DI, and DO all have to be the same as each other. The units for HI and HO have to be the same as each other, but they don't have to be the same across for all 5. Does that make sense? So these could be in centimeters, F, DO, and DI, and then meanwhile HO and HI could be in millimeters. All right, so these are trends. If you haven't been taking notes, I don't know why not, but I would stop the video, go back, write down those notes, and definitely put this list into your notes. So just to go through pretty quickly, we use a positive F for converging lens, a negative F for diverging lens. If you say that DO and HO are always positive, then that's going to mean that DI is positive for a real image, which in this case is going to be on the opposite side. You should have seen that from your chart, that we form a real image, again, when light really converges. That happens on the opposite side of the lens because the light is going through the lens. So that means DI is negative for virtual images, which will be on the same side of the lens as the object. HI, when it is negative, it means it's inverted. When it's positive, it means it's an upright image. This is just like it was for mirrors. Remember, this is slightly different than it was for mirrors. And for magnification, again, it's negative for a real image that's on the opposite side. It's positive for virtual images that are on the same side. And just like with mirrors, when the absolute value of magnification is greater than 1, the image is bigger than the object. If it's less than 1, it's smaller than the object, and I didn't type it in, but you guess if it's equal to 1, it's the exact same size. Okay, so make sure this is in your notes. If it's not, pause the video, put it in your notes, and then keep going. And the cool thing about lenses, I just want to talk about a few applications. You don't have to put this in your notes, although you never know when it's going to show up in a concept question. For example, a lighthouse. So the way a lighthouse works is that you put the bulb at the focal point. And when you put the bulb at the focal point, that means that the light comes out parallel because it's as if the image is at infinity. Why would you want this for a lighthouse? Well, you don't really want the light coming to a point, right? Because that's only going to illuminate like one rock as opposed to the whole cliff. And you also don't want the light to be totally dispersed like what you would in a diverging situation, because then it just won't illuminate anything. You'll just have a lovely spot coming out of the lighthouse. So that's not helpful. For a camera, what you're doing is, and I'm talking about a film camera, you have the object. Let's say I'm taking a picture of you. You're the object, and then the lens, and then the image needs to end up on the film, right, which is on the other side of the lens, and that would be your DI. And so the lens to film distance always is going to be DI, and it's going to be real because you really want an image to show up. And we're going to do a fun lab that you guys can see all this in action. You might remember enlargers. Maybe you used it in a photo class or something like that. The idea there is also using lenses to make an image so that you can make it just show up on the photo paper. A magnifying glass, I have one of those in the classroom I'll show you. That actually creates a virtual image that's much bigger. So that would be a situation where the object is between F and the lens, right? Think that through, look at your chart. There's so many applications. The human eye is a really cool application of lenses. And I think Becca has a fish eye on her phone that we're going to talk about when I see you guys again. Okay, hope you're having a good snow day. Make sure to do your Mastering Physics. Bye.